Hello, everyone. Welcome. I'm Professor Adam Kroom, and the focus of our lecture today will be to complete a machine learning project on DataCamp. The machine learning project that we will be completing today is called ASL Recognition with Deep Learning. In this project, we will train a convolutional neural network to classify images of ASL letters. After loading, examining, and pre-processing the data, we will train the network and test its performance. So let's begin. To start the project, click on Start Project. On the left-hand side, you'll see our project instructions, and we can see that for this project, we have a total of 9 tasks. American Sign Language, or ASL, is the primary language used by many deaf individuals in North America, and it is also used by hard of hearing and hearing individuals. The language is as rich as spoken languages and employs signs made with the hand, along with facial gestures and bodily postures. A lot of recent progress has been made towards developing computer vision systems that translate sign language to spoken language. This technology often relies on complex neural network architectures that can detect subtle patterns in streaming video. However, as a first step towards understanding how to build a translation system, we can reduce the size of the problem by translating individual letters instead of sentences. In this notebook, we will train a convolutional neural network to classify images of American Sign Language letters. After loading, examining, and pre-processing the data, we will train the network and test its performance. In the code cell below, we load the training and test data. Xtrain and Xtest are arrays of image data with corresponding to the training and test datasets respectively. Ytrain and Ytest are arrays of categorical labels corresponding to the training and test datasets respectively. Our first task is to import packages and set NumPy random seed. We also have to load pre-shuffled training and test datasets. And we see that the code has been provided for us, so all we have to do for task 1 is run this cell. And next, now we're on task 2, which is visualize the training data. Now we'll begin by creating a list of string valued labels containing the letters that appear in the dataset. Then we visualize the first several images in the training data, along with their corresponding labels. So our instructions for task 2, use matplotlib to visualize some of the images in the training dataset. Assign the labels to a Python list with 3 items, A, B, and C, corresponding to the signed letters that appear in the images. So here we see that there's some missing code, and we want to provide the right code in this missing area. Okay, and so we want to assign labels A, B, and C. So the way we do that is A, B, C. Next, we want to print the first several training images along with the labels. The code for that has been provided. So now we just have to run this cell. All right, very cool. Now we have our training data provided for us in images. So here is a hand, the image of a hand making the letter C in American Sign Language. And we have it labeled here, C. Here we have another image, and this is an image of a hand making the letter A in American Sign Language. And here we see that this image has been labeled A. And over here, we have an image of a hand forming the letter B in American Sign Language. And we see that this image has been labeled B right here. All right, so cool. Now that we've completed task 2, let's move on to task 3. And this task is examine the data set. Let's examine how many images of each letter can be found in the data set. Remember that the data set has already been split into training and test sets for you, where X-train and X-test contain the images, and Y-train and Y-test contain their corresponding labels. Each entry in Y-train and Y-test is one of 0, 1, or 2, corresponding to the letters A, B, and C, respectively. We will use the arrays Y-train and Y-test to verify that both the training and test sets each have roughly equal proportions of each letter. So task 3 instructions, we're going to count the number of A's in the training data set, and we see that the code has been provided for us right here. Next, count the number of B's in the training data set. And since it's asking us to do something very similar to up here, I'm just going to copy the code and paste it here. Okay, but since I want to count the number of B's instead of the number of A's in the training data set, I'm going to replace 0 with a 1. And it tells us right here in the first step of our instruction that assign the variable num_b train to an integer counting the number of times that 1 appears in the Y train, okay? So we're looking for the number of times 1 appears to count the number of B's, and we're looking for the number of times 2 appears to count the number of C's. Okay, so to count the number of C's, we're going to use this same code, but replace 1 with the number 2. All right, next, we want to count the number of A's in the test data set. And to do that, we want to count here, this is the code that allowed us to count the number of A's in the training data set. And so we have a very similar code down here, but we've replaced Y_train with Y_test to count the number of A's in the test data set. So to count the number of B's in the test data set, I'm going to copy that code, paste it here. And this allows me to search within the test data set, and I'm counting the number of B's. So I'm going to replace 0 with 1. And here I want to count the number of C's in the test data set. So I'm going to use this. Sum Y test, 2 equal signs, and then a 2 to count the number of C's. Next, it says print statistics about the data set, and the code's been provided for us. So now we can hit run cell. All right, and now we see that we have 540 A's, 528 B's, and 532 C's in the training set. And we have 118 A's, 144 B's, and 138 C's in the test set. All right, moving right along, we're on task 4 now, one-hot encode the data. Currently, our labels for each of the letters are encoded as categorical integers, where A, B, and C are encoded as 0, 1, and 2 respectively. However, recall that Keras models do not accept labels in this format, and we must first one-hot encode the labels before supplying them to a Keras model. This conversion will turn the one-dimensional array of labels into a two-dimensional array. Each row in the two-dimensional array of one-hot encoded labels corresponds to a different image. The row has a 1 in the column that corresponds to the correct label and 0 elsewhere. For instance, 0 is encoded as 100. 1 is encoded as 010, and 2 is encoded as 001. Now our instructions for task 4, use the built-in Keras function toCategorical to one-hot encode the data. Use the class vector Y_train to assign the variable Y_train_OH to the one-hot training labels, and use the class vector Y_test to assign the variable Y_test_OH to the one-hot test labels. All right, so now we have to type some code to one-hot encode the training labels. All right, so the code we're going to type here is np_utils dot to_categorical y_train3. And this is the code to one-hot encode the training labels, okay? And next, we want to one-hot encode the test labels. So we're going to use a similar code to one-hot encode, but instead of one-hot encoding the training labels, right, ytrain, we want to encode the test labels. So we'll replace ytrain with ytest. And now we can run the cell and move on to task 5, which is define the model. Now it's time to define a convolutional neural network to classify the data. This network accepts an image of an American Sign Language letter as input. The output layer returns the network's predicted probabilities that the image belongs in each category. So our instructions: specify a convolutional neural network in Keras. The first convolutional layer in the network has already been provided in the code. Add a max pooling layer, pooling over windows of size 4 by 4. Add another convolutional layer, 15 filters, kernel size of 5, same padding, ReLU activation. And then add another max pooling layer, pooling over windows of size 4 by 4. Okay, so with that information, we need to provide some code for these 3 empty places. Okay, so let's go ahead and first add a max pooling layer. So how do we add a max pooling layer? In here, we're gonna type max pooling 2D, pool size equal to 4. Okay, and so I got that information over here, right? Because this is the first place we had to do some work corresponding to this first bullet on the left-hand side. And it tells us that we want to add a max pooling layer. So I typed in max pooling 2D, and it says pooling over window of size 4 by 4. And that's why I set pool size equal to 4. Okay, next add a convolutional layer. And so to add a convolutional layer, I'm going to type conv2d. And then filters equal 15. Right, it says right here, add a convolutional layer, 15 filters. Next, it says kernel size of 5. So I'm going to type kernel size equal 5. Okay, and then next it says same padding. So I'm going to set padding equal to same. Okay, and then last it says ReLU activation. So I'm going to set activation equal to ReLU. Okay, and then last but not least, add another max pooling layer. And again, it says pooling over windows of size 4 by 4. And since it's asking me basically to do this again, I'm just going to copy max pooling from up top and paste it down here. Okay, so max pooling 2D, pool size equal to 4. All right, and then summarize the model, and that's how you do that. So we can now run the cell. All right, very nice. And now we have the summary of the model provided for us right here. Great, we're on to task number 6 now, which is compile the model. After we have defined a neural network in Keras, the next step is to compile it. Specify the optimizer and loss function along with a metric that will be tracked during training. Compile the model with the RMS prop optimizer, categorical cross entropy as the loss function, and accuracy as the metric. And we can see in here, it's asking us to compile the model. It wants us to set the optimizer to something, the loss to something, and metrics to something. So we know that for the optimizer, we can use this, RMS prop. So I'm just going to copy it and paste it right here. Okay, and then for loss, we want to set that equal to categorical cross entropy. So I'm going to copy it from over here and paste that right here. And finally, for metrics equals, it tells us accuracy as a metric. So I'm going to go ahead and paste that right there. And now we can run the cell. All right, next we're on task number 7, train the model. Once we have compiled the model, we're ready to fit it to the training data. Use the model's .fit method to train the model. Use the training data in XTrain and the label data in YTrain OH to train the model for 2 epochs. You must attain a final validation accuracy of at least 80% or 0.8. Note that you should get good results by setting aside 20% of the training data to be used as validation data and by using a batch size of 32. Okay, so it says train the model. We're going to use the .fit method. And so we're just going to type in some code right here. Okay, and what we're going to type first is, it says use the training data in XTrain. So I'm going to use XTrain right here. And then, and the label data in YTrain. Okay, so it's telling me to use this as well. So I'm going to copy that and paste that right here. Okay. And then next, it says, note that you should get good results by setting aside 20% of the training data to be used as validation data. So what I'm going to type next is validation underscore split. And it's telling me to use 20%, right? Set aside 20% of the training data as validation data. So validation split equal to 0.2, okay? And if for whatever reason you're instructed to set aside 15% of the training data to be used as validation data, here we would have just typed 0.15, okay? But we'll stick with 20% for this project. Next, it says that train the model for 2 epochs. So I'm going to type epochs equals to 2. And then finally, it says use a batch size of 32. So I'm going to type a batch size equals to 32. And now I can run the cell to train the model. It might take a moment while it's training. All right, cool. And we saw that it did the first epoch and then the second epoch, and we trained on 1,280 samples and we validated on 320 samples. All right, great. Now that we've trained the model, we can now test the model. So we're on to task number 8, test the model. To evaluate the model, we'll use the test dataset. This will tell us how the network performs when classifying images it has never seen before. If the classification accuracy on the test dataset is similar to the training dataset, this is a good sign that the model did not overfit the training data. So now we want to use the model's .evaluate method to evaluate the model. We're going to assign X to the test data in XTest and assign Y to the test labels in YTest OH. Okay, so we see that we need to set X equal to something and Y equal to something. So we know that we're going to set X equal to XTest. So I'll copy that from the left, paste it right here. And next, we want to set Y equal to something, and that something is going to be YTest OH. So I copy it from the left and paste it right there in the code cell. And then we're going to print the test accuracy. So we'll run the cell, and we have a test accuracy of 0.93. So excellent. We were hoping for a test accuracy of over 0.8 or 80%. So it looks like we were doing pretty good here in terms of test accuracy. Hooray, our network gets very high accuracy on the test set. The final step for task 9, visualize mistakes, is to take a look at the images that were incorrectly classified by the model. Do any of the mislabeled images look relatively difficult to classify, even to the human eye? Sometimes it's possible to review the images to discover special characteristics that are confusing to the model. However, it is also often the case that it's hard to interpret what the model had in mind. All right, so for our last task, we're going to visualize images that were incorrectly classified by the model. We're going to use the model's predict method to assign y probs to a NumPy array with this shape containing the model's predicted probabilities that each image belongs to each image class. Okay, and so since this is the first thing we need to do, I'll go ahead and do that on the right-hand side. So y probs equals to, it says use the predict method. So I'm going to go ahead and type model.predict and then x underscore test. Okay, and then next it says get predicted labels for test data set. So it says right here, assign y underscore preds to the model's predicted labels for each image in the testing data set. Note that y preds should be a NumPy array with this shape where each entry is one of 0, 1, or 2 corresponding to A, B, and C respectively. Okay, so we're going to type some code here. Y preds equals to np dot arg max. And then in here, y underscore probs axis equals to 1. And then finally, it says indices corresponding to test images which were mislabeled. So use the ground truth labels for the testing data set, y-test, and the model's predicted labels, y-preds, to determine which images were misclassified. Assign the variable bad text indexes to a one-dimensional NumPy array containing all indices corresponding to images that were incorrectly classified by the model. All right, so what we're going to type here is np dot where y underscore preds y underscore test and 0. And then print the mislabeled examples. So let's go ahead and print the mislabeled examples. All right, so we run the cell and now we have a printout of the mislabeled examples, right? So this shows us the images that were incorrectly classified by the model. And we can see here that this image was incorrectly classified by the model because the model predicted A, but we see that this is B, okay? The model predicted B, but we see that this is A, and the model predicted B, but it's A, and so on. So we see that these labels or these images have been incorrectly classified by the model. Okay, and what we would do is sort of look at the mislabeled images and see if there's any characteristics that can help us understand why they may have been mislabeled. And what we can do is, if we find any characteristics through a visual inspection that helps us refine our model, then we can go ahead and do that. But as it was noted right here, it's not always possible through a visual inspection to figure out exactly what's wrong with our model, okay? But this is how you can look at the images that have been incorrectly classified by the model and carry out a visual inspection to see what you can gather, okay, from these examples. All right, now that we have completed all the steps for our machine learning project, let's go ahead and check our project. And by hitting check project here, we can go ahead and go through each task and verify that we've completed each of these tasks correctly. So I'm gonna go ahead and hit check project. And we see that I've got some green lights, which is good. Got the green light on all these. All right, and excellent. Congratulations, you passed all the project tasks. And I have 1,500 experience points for completing that. So great. That completes our machine learning project on ASL recognition with deep learning. To review, in this project, we trained a convolutional neural network to classify images of ASL letters. After loading, examining, and pre-processing the data, we trained the network and tested its performance. I hope this lecture was useful for you. Thank you for your attention. Have a great day, and I'll see you in the next lecture.